Okay guys, so we were discussing about until you come, we were just doing some questions, and the question 4 has to be corrected like this, right? I'm just repeating the question. An object of mass 2 kilograms moving with a velocity of 2 meters per second. Correct the question number 4 on the page 1 in the tude. An object of mass, right? It has to be double S. Mass 2 kilograms was moving with a velocity 2 meters per second, collides with another object of mass 4 kilograms, and write this, moving with 2 meters per second to the same direction. Just write it. Underneath, just write object of mass 4 kilograms. Then write there, somewhere in the space, maybe below, 4 kilograms moving with a velocity 2 meters per second to the same direction. Okay. 2 meters per second to the same direction. Okay. If the velocity of the first object was 4 meters per second, find the velocity of the second object. Okay. Right. So let me give you a very quick recap of what we are learning, right? So we are discussing about what? Law of conservation of linear momentum. What is a law? That we could definitely apply in a certain scenario, right? Conservation means what? Something which doesn't change, something constant, right? Conservation of linear momentum. Linear momentum means what? Mass into velocity. That gives the momentum, right? Mass into velocity gives the momentum. Okay. So when can we apply this one? The momentum has to be conserved. That means it shouldn't change. Where's the moment which the momentum is not changing? Yes, we know that when you apply a certain force F, the momentum changes. That means mv minus mu over t. We normally write the rate of change of momentum gives the force, right? So when the momentum change is zero, when there's no external force, if the F is zero, so this into 0 will be 0. So mv equals to mu then. What is mv? Final momentum. What is mu? Initial momentum. So if there's no external force applied, we could write the final momentum is equals to the initial momentum. That's it. So when there's a collision happening, when there's a one object collides with another one, we don't see any external force. There's no any external influence. Just these two objects are colliding, and maybe they could go as a single piece, or maybe they could go as two separate objects but with different velocities, right? Yes. So in this scenario, what we can do, we are equating the initial momentum, that is getting equal to the final momentum. That's what we're gonna do. Okay, let's do it. How? By the way, how many pages that we need to keep there? Could you please count how many pages to the note? Yeah, only for the note. For what we did last day. 5. 5 sides. Okay, just 5 sides. Okay. Right. So it will be 2 into, how do you write the initial momentum? Mass into velocity. That's it. Right. So 2 into 2 plus 4 into 4. 2 is the mass, and this 2 is the velocity, and this is the mass again. This is the velocity. That should be equal to what? Again, 2 into 4 plus 4 into v, right? It's like a grade 10 math. This is 4, and this is 16, and this is 8 plus 4v. Then So it will be 4 plus 16, which is 20, minus 8 is equals to 4v. So v is equals to 12 divided by 4, which is 3 meters per second. Right? I have just wrote the initial momentum of this plus this should be equal to the final momentum of this and the other one, which we can get the v. Okay, simple as this. Right? Sorry again, there are also certain wrong with the question, and now we have corrected it. You got it? Just as a certain idea. Okay, great. Fifth one also. Okay, we'll see. A billiard ball P hits at a velocity 10 meters per second by 10 meters per second on a ball Q which was at rest. If the ball P was moving with 2 meters per second to a direction 120 counterclockwise or anti-clockwise from the original path after the collision, what's the magnitude of and the direction of the ball Q? Okay, let's do it too. Just hold on, I'll find the duster. Miss me, duster එකක අර ලස්සන එකක් දෙලා තිබ්බේ නෑනේ. Sorry, miss. No, it's hidden. Right. Fifth one we're gonna do. Is there anyone who did the fifth one already? You? How about the others? No? Okay, we'll see. Okay, this is that ball P which is moving. Okay, so if you are wondering what is the mass, you might be wondering what's the mass. Do you know what a billiard ball or billiard ball means? Like you just do it like this and like that, and it goes round. I think you have seen all the balls to be identical, right? There's no ball which to be very large and the other ones are very small, right? All of them are the same size. So we can, in the question, it's supposed to give that the masses are equal or maybe identical, but it doesn't mention anything about that, right? You can suppose that they to be identical, but if it is that's my bad, right? I should mention that it should be identical, right? These balls should be identical, which means you can put any mass here. Let's say m. This is the P moving with a velocity 10 meters per second, all right? And there was another ball which is having the same mass, which is the Q, but which is at rest. Okay, this is the before the collision, what's going to happen. And let's say what's going to happen after the collision. We don't know about the P, we don't know about the Q, right? We don't know about the Q. This is the Q, but it mentions something like this. The P, after the collision, it was moving 120 degrees anti-clockwise from the original path. That means it's supposed to go with this path. It was following a horizontal path like this, right? Now it is moving to which side? 120 degrees, which means it's a obtuse angle somewhere here, right? 120. This is the ball P and the mass M. With a velocity 2 meters per second. Okay. Then we are supposed to find the magnitude and direction of this thing right here. Okay. Okay. So if this is 120, what can you say about the other angle measured from the other side? This side? 60, right? Yes. So if it is 60, what we can do? We can quickly resolve this one. That means split this one to two known directions, which we call as the resolving, right? What we can do? 2, what component comes to here? What is this component? 2 Come on, guys. 2 cos 60 towards the angle cos. 2 cos 60 away the angle sine. Then this one 2 sine 60. So we can split this one, this vector, into two directions, which is 2 cos 2 sine. That's it. Okay. So what should be the direction of this thing then? We are not sure about it because it could be inclined. Why? Because this is also inclined, but originally it was moving with a horizontal velocity. So this one could be moving to this side, maybe, we don't know. Let's put it as Vx, and let's put this one to be the Vy. Right? We are not worrying about it too much because if you get either of these to be negative, that means it is to the other side. We can just mark it, right? So here I have marked the components. We can easily find out the components, and later on we can find out the resultant, which is going in the middle, like this. Yeah, that is our ultimate goal, and also we need to find the direction as well, which is the alpha or something like that. Okay, let's do it. How? We can applying law of conservation of linear momentum. We can write that abbreviation, right? Which side we need to put it? This is kind of inclined, so we have a horizontal effect. Also there's a vertical effect. So what we can do? We can apply the conservation law to two directions. One is to the vertical or the other one to the horizontal. We'll put it first for the horizontal. Then I can write m times 10 plus m times 0. You don't need to even write this one. If you're pretty sure about it, you don't need to write it, right? And m times, okay, I'm writing something like this, 2 cos 60. Is it plus or minus? I'm applying it to this side, but it is to the other side, so it will be minus, plus m times Vx. Alright, so you can see the bolts to be identical, so which the m's are cancelling off. We have this side to be just 10, that is equals to minus 2 into cos 60. That's cos 60. Half plus Vx. So this 2 cancels off. There's 1 remaining, taken it to the other side, gets plus. So Vx equals to 10 plus 1, which is 11 meters per second. Okay, so we found this to be 11 then. Similarly, you can apply to the vertically direction, maybe downwards. Yeah, why don't you try that? Shall we? Okay, you got 11 this one. Okay, let's try. This is the question number 5 that we are doing. I'm guessing, yes, 5. Okay, you should get this one. I think last day I gave you this root 31, the value of root 31. Not to remember, but I just gave it for a certain question. Okay, guys, finish with this. Shall we try one more question? How about the eighth one? Just read the question, will you? If you haven't tried it. Okay, it says something like this. A mass of 2m, okay, there's a mass 2m. It is placed on an inclined plane of height 0.8 meters carefully and released such that slide without rolling to collide with a mass, okay, to collide with a mass simple m which is at rest. The two balls then will project to a carbon paper. Okay. First question, it is asking calculate the velocity of the 2m once it is reached the horizontal plane after it is been released. Okay. So let's just first understand what the question is, right? There's a mass of 2m, right, which is placed on this inclined plane like this, which is of height 0.8 meters. And there was another mass which is at this point and at rest. Like this. That's the first case, right? Okay, so what's normally gonna happen if you keep something on a horizontal flow and released it? May I borrow this book? Okay, you could see that if I just have this horizontal plane, okay, maybe like this, right? The horizontal plane like that, and if you keep something, what's gonna happen? It's gonna roll, right? Here it says it's not rolling, but it just slides down. It just slides down so that it is getting a velocity at this point, which is the moment it reached the horizontal plane here. It is being kept on an inclined plane. Now it slides down and gets a certain velocity. Gets a certain velocity at here. That's the very first question that we need to find out. What's the velocity that it reached when it just hits the ground? I mean that it has reached the horizontal flow, right? Okay, we should find that. How you do it? What you did? Ah, okay, yes. So there are a couple of ways that we could do it. That means either we could find out the acceleration of this object through this thing, right? Through this horizontal plane, and you can find out the velocity here. Or else the simplest method that we can do, we can maybe use the theory that we learned from the O levels. Can you remember we kind of could write the energies? We can learn it back again, but what we could do here is since we don't know about it, yeah, we could. What can we do? We can do it in the hard way or the easy way. What we can do? Uh, since we know about the linear equations, we'll just go with that. Okay. Suppose that we don't know about the energy, then we can go with the equation. So let me put this one to be the theta, and this length to be the let's say s. All right. So we should find out what is the velocity at here, which means we need to find out what is the if you know the acceleration of this object through this thing right here, right, through this horizontal through this inclined plane, we could find out the final velocity because the initial velocity here is 0. We're supposed to find the final velocity, right? Okay, so since we know about, we are kind of getting a relation with the s, we kind of know the s. How do you normally find the s? This thing right here, we can write sine theta to be what? 0.8 over s. You guys agree with me? I could write the sine to be opposite over the hypotenuse, right? So I could write then s is equal to 0.8 over sine theta. Okay, so s is 0.8 over sine theta. And initial velocity is 0, final velocity is something we should find out. And what is the acceleration of this one through this horizontal plane? Sorry, through this inclined plane. What's the acceleration? How do you find it? What's that? We know that there has to be an acceleration downwards. That is the g, right? So, what's supposed to be the acceleration along this plane? Yes? How do you find it? Well, I'm going with the hard way, right? There's an easy method to do this, but I'm just going with the hard way. Okay. So you get this to be the G, and we're supposed to find this one. Can you guys tell me what's the angle here if this is theta? We have already dealt with this one. How do you find it? This is theta and this is 90. What's this angle? This will be 90 minus theta, right? How you are getting it? Because we know all the sum of all the interior angles of a triangle is supplementary, or we can say 180. Okay, so from that one, if this is theta, this is 90, we get this one to be 90 minus theta. Okay, if this is 90 minus theta, what can you say about this teensy weensy angle, the inside of this one? This angle is also 90 minus theta. Why? They are vertically opposite. Yes, they are face to face, right? Yes. So this is also to be 90 minus theta. If this is 90 minus theta, this is a line that is perpendicular to the surface. So what can we say about this angle then? This is 90 minus theta. This is 90. Then this should to be back again theta, right? Okay, that is how we are getting that theta right here. So we are getting here theta. So if I just resolve this g, which is the gravitational acceleration, to this side and the towards the plane, this is perpendicular to the plane and this is along the plane, I get what? G towards the angle, what? G cos theta. So this is g cos theta. This is what then? G sin theta. Okay. G sin theta. Okay. So that's supposed to be the acceleration along the horizontal plane, G sin theta. Okay, so with that being said, what's the equation that we can put? What's the linear equation that we can put to find out the V, if you know the U, S and A? V squared is equals to U squared plus 2AS. You might find this on Greek, or maybe you have heard this one already. You have? No? Okay. These are the equations that we are using to find out the linear motion, right? We are using with the linear motion. How about you guys? Have you heard these equations? Okay, okay. Then we're supposed to find the v, initial velocity is 0 plus 2 times, what is the a? That's g sine theta into s is what? 0.8 over sine theta. Luckily you could see the sine gets cancels off. It's v squared. So v squared is equals to 2 into g is 10 into 0.8. That is what? This is 8. 8 into 2, 16. Oh, lucky we are, right? 16 root, that is 4 meters per second. Right? This is actually the hard way that we could go. Is there an easy way? Yes, there's an easy way. But that we need to know the conservation of energy, which we're going to learn in a future lesson. But to give you a certain idea, let me tell like this. What can you say about the energy in both cases? If there's no loss of energy, whatever certain energy has to be there equal to, in a certain movement has to be equal to the next energy. So you can do this one. I think that will mess you up, but anyway, it's potential energy 0 level, you can take it. This is an alternative method, right? So what we can do there, initial energy is getting equal to the final energy. So initial energy will be this thing. What's the initial energy we have? It is at rest, but it is in a certain height. So when you have a certain height, what sort of energy here that you could see? Like mgh or something like that? What's that? potential energy, right? Yes. So that will be mgh. And what's the final energy that we are getting here? If it slides back and reach to the very bottom level, we get the potential. Now here we have kinetic energy to be 0. This is potential energy and this is kinetic energy. That should be equal to the potential energy at the final moment. That will be 0, and also we should have a kinetic energy. That's be the EK, and this is PE, potential energy. Then what? M's are cancelling off, so G times H is equal to half V squared. G is 10, H is 0.8, is into half into V squared. So V squared is equals to, again we are getting the same thing, right? 2 into 0.8 into 10, so V is equals to root 16, that is 4. You can equate the energies and get the velocity at here, or maybe you can stick with the linear equations and you first found out the acceleration along the plane, that is g sine theta, because this is exactly g, this should be g sine theta. We found out the initial velocity. Actually we need to find it, we don't need to find it out, the initial velocity is already given, it's at rest, right? So u is 0, v is the thing we should find out, we know the acceleration, so we are going to apply the v squared equals u squared plus 2s along the plane. Okay, let's copy down. This is the answer for the first question, and this is the alternative method. Still the first question that we have done, right? I think you can guys try the second part if you have finished the very first part. Second part, something we have already found out. This g sine theta. So how do you find it? The sine theta got cancelled off in this scenario. Yes. How did you do it? Okay. Alright, moving to the next part. Gonna just this, right? Let's see. So the acceleration of this one along the plane has to be this, right? A is equals to g sine theta. We know the g, but the issue here is we don't know the sine theta, right? Well, how we can find that one out? We know this height. Do you have a clue with that? No? Well, there's a way again, but I'm just thinking of we could do it in a way that we already know. But let's just keep the second question for a while, right? Just keep it so that it will save the time. We'll move into the third part. If the height between the paper and the edge of the table is 1.25 meters, find the time taken to reach each match to the paper. That means this is the end of the table, right? The edge of the table, the very edge. And what's going to happen? There's a carbon paper that is being placed here. Why do we have a carbon paper? What if, I think you have seen the carbon papers, right? You have? Yes? Okay. Maybe this one. Miss me carbon color. Like this one, right? So what's gonna happen if you just keep a paper here, place the carbon and hit on that? Place the dots, right? Same thing gonna happen in here as well. There's a plane here and a carbon paper is being placed. So once that these two balls reach to the carbon plane, it makes two prints, right? That's what's gonna happen. Okay. Now return this back. So what exactly gonna happen here will be, now it is being placed on a horizontal on an inclined plane. It slides down and gets a velocity here. What's that velocity? We found it to be 4 meters per second with the mass 2m. Now what's gonna happen? It's gonna eventually collide with this, and both of them are falling down. Will be falling down into this carbon paper, and there's another paper that is placed underneath, so it makes two prints. That's the simplest idea that it says. Okay, so if the height between the table and this one to be 1.25 centimeters, I'm guessing, yes, we should find out what's the time taken to reach both balls to the ground. Here this one deals with what? This is, even though these guys will be having a certain horizontal velocity, are those having a vertical velocity? No, right? Both of them are moving like this. They were moving like this to the horizontal direction. There's no any component to the vertical, but once after they escape out from the table, what's gonna happen? Like this. Let me show it slow motion. It's gonna go like this and gonna fall down, right? With its horizontal velocity, while it is falling down, it moves forward. So what sort of a motion is this? We call like this motion. See this one? You see a curved path. What's the name for that? No. It is being called a projectile motion. Have you learned about projectiles before? No? It is called projectile motion. We have two motions that we could see. If it is going like this way, the object is falling down. At the meantime, it is moving forward. That is why we could see a curved path, right? Okay, so that we have already considered. We'll see. If you could have some time back to cover up those parts, we'll see, right? Okay, so both of these guys are falling down. So what brings the objects downwards? This one? Downwards? What brings that? The gravity, right? Yes. So even though they will be having two different velocities, they will fall down under the gravity. So I could apply downwards. What are the things we know? Let's say, do we know the initial velocity? Yes. What's that? 0. Why is it 0? This is having 4 now. Those are to the horizontal. There's no any component to the vertical down, right? So the initial velocity is 0. Final velocity doesn't matter. We know the height that it should fall, that is this one. We know the gravity acceleration, that is the gravity downwards. What else we know? What are the things we should? What's the thing we should find out? Time taken, t. Okay, throw me a suitable equation that we could put there. We know the u, we know the h, we know the a. We should find out the t. Yes, we could apply s equals ut plus half at squared downwards we know 1.25, this is 0, t plus half 10 t squared. 1.25, that is equals to 0 plus 5t squared. So t squared is equals to, this should divide by 5. 125 divided by 5, that will be 0.25. So t is equals to 0.05 seconds. Okay, right. Is it? Zero 0.5. So is that make 0.25? Okay, let's copy down. Yeah. It's better you could just sketch this one on the same diagram that you have already drawn, right? Still, there's no place to apply this conservation of linear momentum, right? It deals with the it, de it deals with the linear motion. Let me know if you find anything difficult or hard to understand. Right? Okay. Moving into the final question. Fourth part. If the separation between the two marks is 25 centimeters on the carbon paper, that means both of them has reached here. I'm gonna erase this part, right? So both of them has reached the ground. Then separation of this one will be 25 centimeters on the carbon paper. Find the horizontal velocities, find the velocities obtained by each mass after the collision. Okay, how do you do it? Now this is the thing gonna happen. See here, there's one ball like this, another ball was sliding down and hits on this, right? Then what's gonna happen? Both of them will be thrown out, but they were having different velocities, right? Let's say after the collision, two m, this is having 4 meters per second, but let's say after the collision, this is having u and this is having v. Let's say like that, right? Then until the moment it reach the ground, both of them will be having the horizontal velocities u and v. Why? Because the horizontal component is not affected by the gravity, right? Gravity is pulling it down now. There's no any component to this side, which means whatever a certain velocity, it will be going straight away like that. That's how the projectiles work, right? Okay. So what we can do, we can put for the, let me write it above, for the 2m to this side, s equals ut. Why s equals ut? Because it is moving with a constant velocity, right? The velocity doesn't change. Okay, so that will be what? Let me put here r1. Okay, so r1 is equals to what? U times t. What's the t? Time taken. Yes, we have already find it out. Why? Until the moment it reaches the ground, that means until the time it takes to reach the ground, it flies horizontal as well. So the time will be, which we have already found out, 0.5. Great. That's the only thing we can do. Then for the m, again to this side, s equals ut. Now let me take it to be r2 from here to here. That's to be r2, that is equals to what? V times 0.5. At the same time, this is having a greater velocity, that is why it should go somewhat ahead than the 2a. Okay, so we could write this to be the first equation and this to be the second equation. What if I subtract 2 by 1? Then I'm getting r2 minus r1, that is equals to 0.5 minus u into 0.5. What is this r2 minus r1? This is r2, this is r1, and we found that it to be 25 centimeters, that is equals to 0.5. I'm going to take it out, v minus u. 0.5 means half, and let me convert this 25 to meters, and that should be equal to v minus u. So I can multiply this to this side. So v minus u is equals to, it will be 50, so it will be 0.5. I'm taking this one as the third equation. Still we can't find out the u and v, but we should find it out. We have two unknowns but one equation. If you could have another equation, we could find the u and v, right? How we can find out another equation? That is the place we could apply the law of conservation of linear momentum. Where? You can see there it is been colliding at this moment, right? So for the collision between 2m and m, I'm gonna apply to this side, applying law of conservation of linear momentum. Initially the 2m was moving with a velocity of 4 meters per second. We already found it. See this one. And the m was at rest. That should be equals to, we wrote that 2m is getting the u while the m is getting the v. That's how we wrote it, right? This is after the collision. Okay, so what? This is 8m equals 2mu plus mv. M's are cancelling off, so 8 is equals to v plus u. This is the fourth equation. Okay guys, we have two unknowns, two equations. What we can do? We can simplify them simultaneously. I'm letting you to do it. Give it a try. Did you do it like that? Great. I think you need to draw it back, right? Better you could just draw it back. Otherwise, you can't mark this R1 and R2. Quickly sketch it back. I think that is great. By sketching it, let me just modify this one a little bit, just a little bit, right? Sorry, this one. Oh guys, sorry. This has to be 2u, right? Oh, yeah. A plus 2u, yes, then it should be 3 into 2 plus this. Oh, yeah. So it is 1, 8 plus 1 equals 3v. Yes, v is equal to 3. Oh, that's so nice. And by 4. 2.5. Is it? Multiply the 3 by 2, right? 2 into this 3. Okay, guys. I'm really sorry if you got scared with this one, or maybe totally fed it up, right? Well, it's a kind of a combination between the conservation of linear momentum and also the linear equation, so the linear motion which we have already considered, right? I'm not trying to scare you, but this could be a creative question that we could get for a maybe for an exam, right? Not for the A levels, of course. A levels will be much harder than this. These are like lollipops, right? A little lollipop that we have a kind of a nice wrapping. It takes some time to wrap up. That's the only difference. But the examples that we try while doing the class, those are like little cinnamon, right? Not even the lollipops, right? Little chewing gums and all, right? We could just tear it up and eat. But these are kind of nicely wrapped lollipops. But the A-level questions will be kind of chocolate ghettos, right? Takes a lot of time to make and a lot of time to consume, but having a real taste rather than these, right? Okay, so don't worry too much. We're gonna eventually, I just need to show you how the steps that we could follow when you are doing these kinds of questions, right? Not to scare yourselves again, but my recommendation is just try it back after going home, right? This is something that you have done based on my guidance. But if you are not practiced enough to do a similar question yourselves, I think doing this question back again will give you the kind of the strength to do it, right? Let's say you are maybe observing a certain person doing something. Let's say there's a tailor, right? And maybe sewing some clothes, right? you're just seeing at that and you might say, okay, this is pretty easy, and you just need to cut it by this and you just need to sieve it, right? Or maybe you are seeing maybe a cook, or maybe what do you call, a person who's making a cake, baker or whatever, right? Now you can see that the baker is putting the flour and all, measuring them up and making the cake. And let's say you are watching a YouTube video, apayamma, right? Who knows? Then in that case you might see, okay, this is pretty easy, you could just do it. But once you're trying to do it, then you see that it's kind of hard to do, right? Because you don't have the practice. So you could see here, all right, once I do it, okay, okay, that's fine, okay, we got the answer like that. But if you are trying yourself back again, you might feel it's kind of hard. That's why I'm just recommending you, once we do some questions in the class, the examples, just try it back for yourself, right? Without seeing the question, without seeing the answer, just try it back. Try to memorize that what we have done. Then if you just try it, and if you can't do it, refer it and close the book back again. Without seeing the book, just try it back again. That gives the practice to do these kinds of questions, and also to think kind of logical, right? That's how you need to increase your practice. Okay, with that being said, I think we can move into the next part of the lesson, right? So we have applied the law of conservation of linear momentum for the collisions, but there are other scenarios that we could apply it. Now we are okay with the collisions. Let's go to the other cases. Let's try the second scenario that we could apply, the second instance. I think we have already applied the law of conservation of linear momentum for the collisions. You can see we have wrote a similar topic, right? So today we are going to consider how we can apply the law of conservation for the linear momentum for the objects which are throwing apart. Okay, we write that one as the next scenario, second case. Applying the law of conservation of linear momentum. I'm just being lazy to write it. Conservation of linear momentum for the objects thrown apart. That's a very big topic, right? Kind of lengthy. Let me repeat the topic again. Applying the law of conservation of linear momentum for the objects thrown apart. Alright, let's write like this. Let's consider two masses. After the topic, you can write like this. Let's write. Let's consider two masses, capital M and simple m. Consider two masses, capital M and simple m, attached by a string. Attached by a string. Compressing a spring. Oh, kind of rhyming, right? Compressing a spring at the middle. Okay, it's something like this. You have a spring, then you're gonna compress it, and you're gonna keep that capital M on one side and the simple M on the other side, and attach it by a string. Strings, kind of rhyming, right? This is the string. This is the string. and this is the spring. I think it makes sense, right? Now the spring got compressed and the string is attached. Now what's going to happen if you cut this one, the string? It's gonna toing like that, right? It's gonna throw apart. The simple name. Now once this is being thrown apart, they will get a velocity. Let me take this one to be the v, this one to be the u. Alright, so do you see an external force here? Now this is the string, it got cut. Do you see an external force here? No, right? Once you just cut it, we are not trying to make it apart, or we are not going to compress it, right? We are not applying any external force, thus the linear momentum should be conserved. Is it? Yes. That's what we are going to do here. Okay, let's copy down. Just mark that this string is being cut. Now they are thrown apart. Okay, we write after the string being cut, after the string being cut, after the string being cut, the compressive force of the spring, the compressive force of the spring throws the two masses outwards, throws the two masses outwards, throws the two masses outwards. Even though there are internal forces, even though there are internal forces, even though there are internal forces arised in the system, arised in the system, arised in the system, there's no any external unbalanced force, there's no any external unbalanced force applied on the system. Applied on the system. Thus, the linear momentum is conserved. Thus, the linear momentum is conserved. Right. So we're gonna applying the law of conservation of linear momentum. We can apply to any direction. Let's put this side or to the other side, whatever. Right. Okay. Tell me, what is the initial momentum of the system? Yes. Why is it zero? We have the capital M having no velocity. We have the simple M also not having any velocity, right? But what's going to happen afterward? After this string is being cut, both of them shoots out. So M is having a velocity of u, or let me put with the capital M. Capital M is having a velocity v, but you can see that I have applied to this side, and this v is to minus, right? To the other side, so it is v minus. Plus m times u. So I get 0 in this side, that is minus mv plus mu, right? So I can take this mu to this side, mv is equals to mu. Okay, let's copy it down after that. Okay, then we'll write, since the initial momentum of the system is 0, since the initial momentum of the system is 0, since the initial momentum of the system is 0, the two masses going to the opposite direction, going to the opposite direction, going to the opposite direction, which with the momentums equal, with the momentums equal, with the momentums equal, to keep the final momentum of the system, to keep the final momentum of the system also to be 0. Right. So what's gonna happen here? We could see that initially there's no any momentum. So in the final system also we shouldn't have any momentum. That means if the initial momentum is 0, the final momentum has to be also 0. To make the final momentum 0, what's going to happen? Whatever a certain momentum gets, this one should cancel off by the other one. That is why we could see mv should be getting equal to the mu, which means the momentum of these two has to be equal in magnitude but should opposite in direction, like a EG plane does, right? Should opposite in direction. Then what's going to happen? They should cancel off, making the initial momentum again back to 0. Okay. So we'll write as a star mark and write like this. Put a star mark. Here, the higher mass gets a smaller velocity. Here, the higher mass gets a smaller velocity, while the smaller mass gets a higher velocity. While the smaller mass gets a higher velocity. Okay, let's say this one. Let's see, this is to be 5 or maybe 10 kilograms and having a velocity of 4 meters per second. That's what? 10 into 4. That is 40, right? What if this one to be 2 kilograms? So 10 into 4 on this side gets 40. So this should get 2 into what? To make the same 40? 20. So see here, higher the mass, smaller the velocity it is. Smaller the mass, higher the velocity it gets. Which means the smaller guy will shoot up faster than the guy with the higher mass. Right? Okay. That's something you should see. Alright, we'll write another star mark. I know it's a lot of notes, right? This is the last piece here, right? When shooting through a gun, or when shooting by a gun, the gun recoils back. Recoils back. Following the same law of conservation of linear momentum. Okay, so when shooting by a gun, I think you may have seen this. Let's say this is the gun, like this. Well, I'm not good at drawing guns, but maybe this is to be the gun with the capital M. Okay, so there's a bullet inside. G7, let's say simple M, right? Once it is being shot, what's going to happen? The bullet should move forward, right? The bullet should be moving forward with a certain velocity, right? What can you say about the initial momentum of the system? 0. The person is holding just the gun and the bullet was inside the gun, right? But after it is being shot, the bullet is moving forward with a certain velocity. That means it is gained up a certain momentum, right? but that momentum wasn't there before. And this is being shown with the internal explosion because it is exploding internally, right? With that gunpowder and all, it is being exploding internally. So there's no any external force applied on it. So you can see that it is gained a certain final momentum, but initially there wasn't any. What should happen? This should cancel off. To make it cancel, what should happen? The gun should move backwards, which is called as recoiling, right? Or we say the backfire. Have you seen when they are shooting, they just like that? So the gun comes back while shooting. Can somebody shoot like this, like that? Even that, the hand comes, right? Can it shoot like this, like that? No, right? At least the hand shakes. Why is it so? Because while the bullet is leaving, it gains the initial momentum. Sorry, it gains a momentum which is not been there in the system. So to cancel it off, they should move backwards. But again, we know that smaller the mass should get a higher velocity. Higher the mass it is, should get a smaller velocity. Otherwise, what's going to happen? Once you shoot it, the gun and you throws backwards with the same speed of the bullet, right? Then you can shoot to the other side while the bullet goes to the front, right? That won't happen. That is why if you have a higher mass with the higher gun, you have higher mass of the gun, smaller the recoil it is, right? Smaller the gun, it gives a higher recoiling. We call it recoiling of the gun. So normally when you go to, let's say you prefer to go military, right? They are been training for 6 months for weapons. We call weapon training, right? For those 6 months, they are training to hold this backfire. We call the backfire for almost around 4 months because handling that backfire and keeping the target is the very hardest thing that you need to experience there, right? Because it is being recoiled back, so you can't keep the target while it is recoiling, right? That's the one being practicing for almost 4 months. Afterward, they can shoot to the targets, but before that, they need to hold for the backfire, right? Okay, I think you got the scenario, right? Next day, I'll show you some funny videos, or maybe I can share to the our group, right? If it is not being correctly handled, the gun, it throws back, right? Okay, let's draw it. You don't need to draw AK-47, right? Just a gun. Okay. So next time when you watch a movie, just see the physics behind those. Right? Okay. We'll get out an example question. Find the recoiling velocity of the tank. Find the recoiling velocity of the tank. Find the recoiling velocity of the tank while the bullet is being shot, right? Okay, so there's a tank here shooting a bullet. That could be the mass of the bullet. 2 kilograms, let's say. And it's shooting very fast, hypersonic, let's say 1,000 meters per second, or maybe 100, yeah, let's be practical, 100. And what could be the mass of a tank? Let's make it 2,000, which is 2 tons. Okay, you're supposed to find the recoiling velocity of this tank to be backwards. Just find it out. What do you got? 10. 10. Isn't it supposed to be 0.1? Why? Is it? Yes. You can either put MV equals MU, so this into this should equal to this into this. You put the mass of the tank to be 200. Yes. Okay, great. Okay, let's do one more example and we're gonna have a very short break, right? One more example. We write like this. The A and B, the A and B which is 20 meters away, which is 20 meters away, approach each other. Approach each other pulling the string. Pulling the string. Find the distance traveled by each trolley. Find the distance traveled by each trolley when they hit each other. Okay, so let's say two children are there. Let's say this is A and this is B. A girl and a boy maybe pulling the strings. There's a string in the middle. They are going to pull each other and what's going to happen? Eventually they will approach, right? Okay. Let's say this is the B which is having 30 kilograms. A is having 20 kilograms maybe. The girl is having high weight, right? Okay. So we're supposed to find initially they were at 20 meters apart. So we're supposed to find once they hit each other, the trolleys, right? How far the A has traveled and the B has traveled. How do you find it? Is it the same scenario like the two masses moving apart? Well, not moving apart, but here they are approaching. Could be the same. Why? Because there's no any person who's pushing these trolleys, so there's no any external force, right? Neither for this girl with the trolley. So what's gonna happen? There will be two internal forces which are the tensions of the strings, but they will cancel off. So we could still be able to apply the conservation law, right? Let's see. So what we can do here, let's put the distance the A has traveled once it is being hit to be X, then how far the B has gone. Yes, 20 minus X. Okay, let's sketch it first and think about a way. Shouldn't be the Jack and Rose in the Titanic, right? Just draw any two figures. Okay, so we should deal with a certain displacement, but we can write in terms of velocities, right? We'll write it first. How? Applying law of conservation of linear momentum, maybe to this side. Initially, both of them were at rest. Now, so there has to be 0. Finally, we are applying to this side. So A is having, let's say, MA, that to be having a UA velocity, plus MB having a velocity of UB, but it is to the opposite side, right? So I could write MB UB is equals to MA UA, right? Or simply MA UA equals MA MB UB. That's the one we wrote already. MV is equals to MU, right? When they are moving apart, right? Okay, so the mass of this B is that girl, which is 30 times UB, that should be equals to 20 times UA, right? But the thing here is we shouldn't need to find the velocities, we need to find the displacements of them. It's asking how far the A and B has traveled when they meet each other. So how you can relate a displacement to a velocity? Yes. How do you find the velocity in terms of displacement? Yes. We know the velocity is equals to displacement divided by time, right? So I could write this velocity UA in terms of what? How far the A has traveled? X. And at the same time, how far the B should travel? 20 minus X. Yes. If the time is T, if the time taken, if I write here, can you see, guys? If the time taken for the collision or to meet each other be simple T, during that time what's going to happen? I'm going to write here, or maybe down, right? During that time, 30 times UB, I could write 20 minus X over T. 20 into UA, I could write what? The displacement is X. Within the same time, it goes like that. Alright, so how to simplify this? 30, 20 minus X over T, that should equals to 20 into X over T. We can see the T's are the same. It's the same time taken for the both guys to reach. So the T's cancels off. It would be 30, 20 minus X, that is equals to 20X. Now simplify this. We'll simplify the brackets. Take the X to the one side, and we can do it. So it will be what? 600 minus 30X, that is equals to 20X. So I can take this 30 to the other side. 600 is equal to 50X. 0 cancels off. X is equals to 60 minus divided by 5, that is 12 meters. So if X is 12, you can say with the B, 8. It's traveling 8. See, the smaller mass gets a higher velocity. That is why the A could go faster, right? A is going very faster than the D. Okay, copy that. This is how we can relate the velocities with the displacements. After you getting this all, you can write A, displacement of A equals 12 meters, displacement of B equals 8 meters. Okay. Right. So as I promised, we'll have that 5-minute break. Don't go far, right? You can maybe wash your face, refresh you up, and we're gonna finish the class by 4. So now it's 3:06. Come back by just 3:12 or 11 like that, right? Okay. Go around and count. Right. So in this case, we see some inclined velocities, right? What is the thing we normally do when you see the inclined velocities? We resolve them and to make it to two known directions, right? Which are the horizontal component and the vertical component. What is the horizontal component? Yeah, let's say it together. V2 cos. V2 cos. Good guys. Cos alpha. This is what? V2 sine alpha. Okay. V2 sine alpha. What about this one? V3 cos beta, right? This is beta. So you know what beta means, right? Just B with this extended letter, extended leg, right? So that is V3 cos beta. This is V3 sine beta. Okie dokie. Now what we can do? Still, we don't see any external force. No one being pushed this one. It's just exploding. It's due to its internal some sort of a reaction or something. We don't know, right? Since there's no external force applied, we can apply the conservation of linear momentum. Here you could see that it is being inclined. Some velocities are inclined. So what's the best way? We could apply to our two known directions. Which are the two known directions? Horizontal and vertical. Let's apply. So I can apply to this side. First for the horizontal, applying law of conservation of linear momentum. Initial momentum m1 plus m2 plus m3, all of them had a velocity of 0. Let's say this one was moving up, then you should apply that velocity, right? Here in this case it is 0, so you need to apply it. It was at rest, like maybe a bomb which is at rest. Okay, now final momentum m1 0. Why? I have marked the u1 to be vertically up, there's no any horizontal component, plus m2 v2 cos alpha plus m3 v3 cos beta, but that is minus, right? Why? We have applied to this side, but it is to the other side, so it will be minus. Okay. Then we can even apply to the upwards, applying law of conservation of linear momentum. m1 plus m2 plus m3, again it is 0, equals what? m1 u1 minus, I'm going to directly apply that, m2 v2 sine alpha minus m3 v3 sine beta. You could write like that, right? Okay, let's copy it down. Okay. Okay, we can consider the final application as well, right? Afterward, we'll try some questions finishing up this. Okay, next we'll write applying law of conservation of linear momentum. Well, you can write with that abbreviation, right? It doesn't matter. Applying law of conservation of linear momentum. For an object moving on another object. For an object moving on another object. Right, we'll write like this. Or maybe we'll first draw it. There's a trolley, a lengthy trolley with two wheels, and there's a person here standing like this. Okay, let's say the mass of this trolley is capital M and the mass of this man is M. He's just standing on the trolley. Simple as that. Huh. Well, I'm not good at drawing human figures, right? Okay, so what this guy is doing is moving or walking to this side, the velocity u. Okay, tell me what should happen to the trolley. Now the guy was moving, standing like this. Now he thought maybe I could walk. Then while he's moving, what's gonna happen? The trolley? What's gonna happen to the trolley? It should go backwards, right? Like this, like the moonwalk of the Jackson, or whatever. That's Michael Jackson, right? Yes. I could just walk, but it's not moving. Okay. Right. So the trolley has to go backwards. The velocity v. Okay. Let's draw it first. Then we'll write. Okay, shall we write then? Okay, we write the system, initially the system is at rest. Initially the system is at rest. We write initially the system is at rest. When the child start to move forward, when the child start to move forward, the child, sorry, the trolley with the child, the trolley with the child, when the child start to move forward, the trolley with the child should move backwards, should move backwards to maintain the total momentum, to maintain the total momentum of the system constant. Right. Just underline that word, the trolley with the child. You can underline with a red color or maybe any other color you like. The child with, or the trolley with the child. The trolley with the child. That's an important word here. Okay, so we write the initial momentum and the final momentum. So initial, you can write with me, momentum. And I'm going to write the final momentum as well. What's the initial momentum? Yes? Initial momentum? Yes. M and M both were having zero velocities. They were at rest. Equals final momentum. So here also I'm going to apply the law of conservation of linear momentum, right? You should write it somewhere to this side or maybe any direction that you're going to put. So what? This is zero. Final momentum. M times U. This is the important thing. The trolley should move backwards. Just the trolley or the trolley with the child? Yes, when the trolley moves backward, there's the child on it. So the trolley with the child, that means M plus capital M should move backwards with the V. This is the important thing. Make sure you just write the M's nicely, right? This is capital M and this is simple M. Okay, so with that I could write mu is equals to what? M plus M V. Okay, so let's consider an example. Okay, there's a vehicle here, maybe mm, kind of like a caravan or something like that. 20 kilograms, no, 200 kilograms. This is A with it's to be 50, okay, kilograms. This was moving with maybe to be a bus, but a bus should have a higher mass, right? But 4 meters per second, whatever. Going for the second scenario, you can draw with me if you like. Just copy and paste the bus here, the same bus. I should find out the V when this guy over here start to walk with 10 meters per second. Here the guy is not moving. Maybe you can draw it like this way or like moving, whatever. This might be the conductor and he's moving forward. Ticket gunner like that. Moving forward. Okay, so try to find out the V. I'll give you maybe 2 minutes. See you soon. Found it? What is it? 5. Okay. I get 2. Is it? Yes. Why is it so? See here, initially the bus, let's say the bus, to be a bus, okay? So initially this thing and the person was moving with the same common velocity 4 meters per second, like this. So 200 plus 50 into 4. That should be equals to you. Now the person here is moving forward, like that, right? With 10 meters per second, like this, plus what should happen? We should find out the velocity of the bus now. It's not just the bus with the same person, right? Because initially also we have put that 4 for both. So the final also we should put that V for the both. Okay. So it should be 2. Is it clear for you guys? Let me know if you are not getting it clear. All good? Okay. We'll just consider one more questions and we're gonna wind up the session. Okay. Let's try it. Another example question. There's a okay. We'll have a quick election, right? With the pets, who do you like? Cats or dogs? Dogs. Dogs. Cats. Dogs. Dogs. Okay. We're right. We're right. There's a dog on a log of wood. There's a dog on a log of wood floating on water. There's a dog on a log of wood floating on water. Show the water. Just draw it like this. Okay. There's a log floating, and this is the ground. Maybe there's a tree here and a house. Where's the dog? Okay, this is the dog. How to draw a dog? Okay, you can draw with me a dog. The dog is like a goat, but anyway, it works. let's say the mass of this one to be the log will be the 80 kilograms, and this is around 5 meters in length, and the log is 10 meters away from the ground. By the way, what's the average weight of a mass of a dog? Maybe a good one. I mean, Alsatian or maybe German Shepherd. 30 or 20. Okay, let's say 20. Average value, right? 20 kilograms. Just draw the dog somewhere at the end, right? Not in the middle. Just draw any random. Just draw any random dog, right? Doesn't need to be a Siberian Husky. Whatever. Right. Okay. We are right in the very first question. This is the water, right? This is water. Okay. The very first part of the question. When the dog starts to run towards the land, when the dog starts to run towards the land with a velocity u on the log, with a velocity simple u on the log, find the velocity on the log, the velocity u on the log. Let me repeat the question once again, right? When the dog start to run or start to move with a velocity u towards the land on the log, whatever, right? The dog is trying to run towards the land with a velocity u on the log. That's it. Okay? On the log, find the velocity which the log moves backwards. Find the velocity the log moves backwards. Okay, so you can maybe put here v and mark the u, then find it out. Okay, now there's a dog floating on this little wood, right? Piece of wood, the log, and the dog sees the land. Then what it do? Try to run, right, along the log. Wow, wow, like that. It's running. So what's gonna happen? The log start to move backwards. So you're supposed to find the velocity v in terms of u. That's it. How to do it? Now the dog start to run forward, which means 20 into u. That's the initial velocity that we can see. Like mu is equals to m plus mv, right? That's the thing we're gonna put there. M plus m what? 20 plus 80 into v. So v is equals to 20u over 100. That's v equals to 1 over 5 times u. Okay, so the next question, next part of the question. Next part of the question. How far the log has traveled backwards? How far the log has traveled backwards? Oh, actually, not traveled, right? Log has moved backwards, then it's good. Log has moved backwards. When the dog reached the other end of the log, when the dog reached the other end of the log, other end means the dog is running, the other end means 5 meters, right? He's at this side, so he's gonna run into the other side, 5 meters. So when the dog runs 5 meters, we're supposed to find how far the log has traveled backwards. How to do it? Now the dog is at here. We're supposed to find how far this goes backwards. We know both the velocities. One is u, the other one is u over 5. Yeah, any crazy ideas? You can see here the dog is moving at the velocity you know. So what? Let me first teach you the hard way. Then after I'll teach you the easy way, right? So for the dog, let's let the time taken to reach the other end be what? T. So I can put for the dog s equals ut. So 5 is equals to u times t. Okay. So t is equals to 5 over u. Then for the log to this side, s equals ut. So s is the thing we should find out. U is actually 1 over 5 u times t is what? 5 over u. U cancels off, 5 cancels off, s is equal to 1 meter. You're getting it like that. Or else, what's the easiest way? Well, you can see here the velocity of the log is 1/5 of the velocity of the dog. The velocity of the dog is u, velocity of the log is 1/5 of that value. So if the dog goes 5 meters, how far the log should go? 1/5 of it, which is just 1 meter. You can write it like that as well. Shall we write it like that? You can first copy down this one if you need. Right? You can copy this one down. That is the kind of the length method, but still it works, right? Takes some time, but it works. We write like this after getting this one. Since the velocity of the log is 1/5 of the velocity, since the velocity of the log is 1/5 of the velocity, since the velocity of the log is 1/5 of the velocity of the dog, 1/5 of the velocity of the dog, the log should move. The log should move 1/5 of the distance. The log should move 1/5 of the distance run by the dog. 1/5 of the distance run by the dog. Right? Then 1/5 of 5 meters, that is 1 meters. 1/5 of 5, you can write like this. 1/5 of 5, that is 1 meter. Okay. We're going to write the last part of it, and that is the end of the today's session as well. How far from the dog to the land? How far is to the dog to the land now? How far is the distance from the dog to the land now? What is it? 11. Why is it 11? Initially it was 10, but this stupid dog didn't know the no, not to say like that, but it didn't know the conservation of linear momentum. That is why it start to run, right? While it start to run, what's going to happen? It just see the land and start to run. Then the log with the dog should move backwards, right? So now the distance that the dog, between the dog and the land will be what? Even though the dog has moved to the other side, it will be 10 meters initially, plus there's 1 meter the log went back. It will be altogether 11 meters, right? Yes. So initially the dog has to swim. If the dog just walk slowly like that and jump into the water, it just need to swim only 10 meters. But if the dog runs, the log goes backwards, then it should swim now 11 meters, right? Okay. Just write 10 plus 1, it will be 11. Okay, so with that being said, that's the end of today's lesson. Also, the end of the conservation of linear momentum as well. So whenever you get a question, you can just wrap up and listen to it at the same time, right? Whenever you get a question, just see whether which scenario that is being suited, right? When you get a question like this, let's say this question right here, the 14th one, it explains about something, an explosion, right? So just consider the scenario which this one is being suited and apply it accordingly. And one more special notice, guys. Next week it will be a poet day, the Sunday. So normally for the poets we are not doing the classes, except we did it for one day, right? Last month, I guess, right? So which gonna be a holiday for you? If you are getting a holiday for the Saturday as well, you can maybe go around, see the stuffs, and maybe like have a visit somewhere if you need, right? Because you're gonna be having 2 holidays if you have a holiday for the Saturday as well, right? So Sundays we are not meeting each other. We're gonna meet by the next Sunday, right? We'll try our best to arrange an extra class, but for the time being, after schools, this class is being occupied, right? We'll see. I'll let you know for the group, right? Okay then. Thank you for joining the class and have a great week. Okay, see you then.